Welcome to premise course number 108, and today we're talking about vertical airfoil end plates on diffusers in vehicle aerodynamics. So let's talk about what these things are to begin with. So a diffuser is a object. Let's say we have the ground here, and then on top we have an object which then at the back starts to go up, and it could go up in a fairly linear way, or it could go up in a rounded way, or whatever that is. There is an expansion of the cross-sectional area. So the cross-sectional area at the end of the object compared to the ground, so let's call this A2, compared to at the start or anywhere else, is greater. So what that means is that the air then has to expand in terms of its like actual constituents. So that's a diffuser, and we find these things on all sorts of aerodynamics, such as cars and also in turbojets, for example, the nozzle of the exit, the nozzle, and etc. So vertical airfoil end plates are kind of what they sound like. It's a little bit difficult to conceptualize, but imagine an airfoil, and then on the end we have end plates, and they can be kind of seen as like sharklets or winglets or whatever. That's some kind of end plate, and then they go vertical, so you have like a horizontal object, for example, and then you have these end plates on the end, and now they're actually an airfoil profile. So instead of just being a flat plate, they actually have an airfoil cross section. So that means that they could be like a NACA 0012 or whatever, but that's the end plate there, and they extend down, however it is. So to look at this aerodynamics, we're going to be looking at a paper called Study of the Effect of Vertical Airfoil End Plates on Diffusers in Vehicle Aerodynamics. And this is an open access paper they can find in the link in the description. So let's get on with this investigation. So they start off saying that vehicle aerodynamics contain many downforce generating elements in order to generate pressure differences to push the car's tires onto the road to enhance traction in corners. And this is obviously very important because the faster you can go around corners, the faster you'll complete a lap. And the only way you can really go fast around corners is by having a lot of friction between your tires and the ground. So one way to do that is by increasing the downforce, which pushes the car into the ground. So the three most important elements in motorsport cars for downforce production are the front wing, the rear wing, and the ground effect / diffuser. So the flat bottom along with the diffuser, so the flat bottom of the car, and then at the back when the car, like the bottom of the car goes up, are the elements that generate a great amount of downforce with less drag generation compared to the wings. So for example, for F1 cars, this section, so the underbody and the diffuser, accounts for about 60% of the total downforce of the entire car, but only contributes about 10 to 20% of the total drag. So that shows you just how efficient they are at producing downforce compared to other things such as wings. Even though wings do get a lot of attention, the diffuser and the underbody is a very important part. And one major reason because of that is because it is such a big surface area to begin with. When you think about the actual vehicle, it's a big thing. So compared to with the wings, which are only quite small, just by virtue of the fact that they take up a lot of area, they're going to produce a lot of downforce, and in this particular case, the majority of it. So this creates an advantage compared to other elements, such as the front and rear wings, which have a higher lift to drag ratio, a higher drag to downforce ratio, I should say. It's downforce and not lift here. Downforce obviously being the negative direction to lift, but effectively the same thing. In addition, the outboard shape of the diffuser is also important to prevent disturbances of the rear wheel wakes from entering the central channel. So what this means is how you shape the diffuser, so the edges of it, affects the aerodynamics, and you could result in throwing air where you don't want it to go, for example, into the rear wheels, or have the rear wheel air come into the diffuser. And often the rear wheel air is very sluggish, I should say. And that means that it doesn't have a lot of energy, which potentially will reduce the efficiency of a diffuser. If you can actually even design a diffuser to handle these things to begin with, you may even just get to the point where it just completely ruins the diffuser's efficiency because the vortices coming off of it and the slow moving flow doesn't work properly. So the flat bottom acts as a venturi, taking the air from the free stream to the underbody, resulting in higher velocity relative to the air above the car. So a venturi effect, if you're listening to this on Spotify, you can watch this on YouTube and or Spotify as well. So a venturi effect, I actually talked about this in the last podcast effectively, where I was looking at the contracting, the diverging converging diverging nozzle. So let's say we have, again, the ground, and then on top we have whatever object, and it can be anything really, as long as it just reduces in height to the ground and then goes back up. So what happens is you have the free stream velocity coming in, and as it comes into the area of the inlet, which has a very great cross-sectional area, it's at a certain velocity. Let's say it's, I don't know, 10 meters per second. Then as it travels through the converging diverging nozzle, because the cross-sectional area reduces, the velocity has to increase, because we use the continuity equation, which is the density times the area times the velocity has to be constant. So if the density is staying constant, which we assume it is because it's incompressible, and the area reduces, the velocity must increase to maintain continuity. So this means that the velocity has to increase, let's say, to 20 or 30 or 40 meters per second. Then when you go through the contraction, you then get to the exit, and the velocity will reduce because the area has now increased, the cross-sectional area. So that's the Venturi effect, and it's very famous. So they're saying that the flat bottom of a car acts as a Venturi, taking a Venturi tube, effectively taking the air from the free stream to the underbody, resulting in higher velocity relative to the air above the car. So this also means that a drop in pressure occurs. This effect produces a differential between the bottom and the top of the car, which manifests as an increased load acting on the tires, also called downforce. At the same time, a reduction in the air resistance force, or aerodynamic drag, may take place, thus improving the vehicle's energy efficiency. So you not only get a greater downforce, but you also get a lower drag. So the effect of drag generation will depend on the diffuser geometry. For example, when the diffuser angle is too small or too large, the diffuser will create more drag than necessary. So for example, if it's too large, you can get separation around the diffuser. So most diffusers, at least traditionally, were quite crude in their design. So if you have just the ground again, and then you have the object, and then you have the diffuser at the end, it just like pops up at an angle. So this angle here is very sharp. It's not rounded or anything. So if you have an angle which is too great, the flow that goes around towards the back will try to go around the angle to the diffuser and separate. So you get lots of unsteadiness here. That's obviously drag. So that will increase or reduce the performance of the drag of the car. So hence an optimal geometry will provide an optimal contribution of downforce and drag. To reduce the underbody pressure further, a diffuser is placed at the rear section of the car underbody and consists of a diverging ramp surface. The diffuser's cross-sectional area increases until reaching its maximum area at the rear part of the bottom of the car. So in other words, as you get to the end of the diffuser, that's going to be the point where you get the greatest cross-sectional area, because now the air then goes into the free stream. So this acts as a transitional section where the underbody airflow at high velocity and low pressure recovers the pressure before exiting to reintegrate at the free stream with atmospheric pressure. So let's talk about this, because this is highly transferable to many different topics in aerodynamics, and we'll cover why in a second. So again, if we have the diffuser, we have the floor, and then on top we have the diffuser, and it comes up. As the air comes through, it is lower pressure because it has accelerated, so the pressure drops. As we come around to the diffuser, the pressure will then increase. So we have the atmospheric pressure, which, let's say it's 101,300 kilopascals, which is the standard, although it does change from day to day and hour to hour. But let's just say it's 101,300 kilopascals. When you get to the end, you can, in terms of just basic aerodynamics, you have three different types of exit flow. You can have underexpanded, perfectly expanded, or overexpanded flows. So underexpanded means that the flow is exactly that, it's underexpanded. It hasn't expanded to the point where the pressure equals the free stream velocity. It's actually lower still. You then have perfectly expanded, which means that it is the same as the free stream velocity. Then in this particular case, you have perfectly overexpanded, which means that the area is being expanded too much, and now it's at a higher pressure in this particular case. In turbojets, it's actually the opposite, because turbojets have higher pressure inside the turbine, and then you have to reduce the pressure to match free stream velocities. Sorry, free stream pressures, I mean. What this does is it changes the efficiency of the diffuser or the outlet or whatever you're using. So the ideal case is when you have perfectly expanded flow, which means that the pressure coming out equals the pressure from the atmosphere. If you don't get that, you'll either get the atmospheric pressure pushing back into the diffuser, or you have not used all the energy you could from the flow otherwise. So there are two different cases which are suboptimal. The optimal case is when the pressure coming out equals the atmospheric pressure. So that's what they talk about here. So to reduce the underbody pressure further, we covered this a little bit. Let's move on to the next part, figure 1. So we talk about the armored body. If you've done any aerodynamics in vehicles, you know that the armored body is like the gold standard kind of thing. Like everyone does it because it is a very basic shape, but it covers a lot of the aerodynamics that you find on vehicles. Now, it doesn't cover everything, but it does have a lot of the basics. So that's why there's so much information on it. So in this particular case, the armored body is a standard bluff body geometry first proposed by Armored and others in 1984 to study how adding a slant angle at the back, so the backlight angle of a car, influences the flow field and resulting aerodynamic forces. They show this in figure 1. Initially, it was used like imagine a rectangular prism, and the front is rounded a little bit. Then the back top angle, the back top corner, has now just been chamfered off, so it's now a slant. That's what the armored body is. However, in this particular case, they're flipping this over so that that slant is now on the underside. So as shown in figure 1, with the addition of a diffuser in the rear part of the armored body, 4 characteristic parameters appear. The slant or diffuser angle, which they call Q, the diffuser length, which is called N, the ride height or the inlet height, which is called H, and the outlet height, H2, which is a function of the inlet height and the diffuser angle and the diffuser length, obviously, just from trigonometry. The pressure recovery in the diffuser is improved by the section shape and the end plate fence to produce as uniform distribution as possible in the vehicle longitudinal direction, avoiding local separations. In other words, as I mentioned earlier, you can get bleeding from air coming up from elsewhere, coming in because the pressure is lower under this section, and that can spoil the diffuser's efficiency or effectiveness. So by putting fences, for example, and by making this slant angle not too severe, you can keep the flow attached. So consequently, the objective of this study is to investigate the effects of the diffuser geometry on the armored body with vertical airfoil end plates in order to improve the understanding of flow behavior. So 3-dimensional CFD simulations of armored bodies are performed to observe the behavior of the flow under different diffuser configurations. First, a non-diffuser armored body configuration is studied to act as a reference configuration for comparison. Then a 25-degree diffuser is added at the end of the body for the second configuration. So 25 degrees means that this angle here between, like if you between the underbody and the diffuser slant is 25 degrees. Sorry, I'm actually drawing for those of you just listening, so that's why sometimes I'm talking a little bit slower. I'm just drawing a few figures for people who are watching this to see. Finally, the third configuration consists of the addition of 2 rear vertical airfoil end plates of the 25-degree diffuser. The separation in the areas in which pressure is recovered and the entry of the leading edge separation vortices of the rear tires are factors that reduce the effective cross-sectional area of the diffuser exit. Vertical airfoils amend this. So let's talk about this. They say, so separation areas and the entry of separation vortices of the rear tires are factors that reduce the effective sectional area of the diffuser exit. What does that mean? This is a way of non-dimensionalizing effectively this object. So if you have this object and it has a cross-sectional area of 1 meter squared, for example, but you have vortices coming in, it spoils some of that area. So you can't really have the entire 1 meter square acting 100% efficiently. So you might only have 0.09%, 0.9 meters squared. So that's 10% less. So that's what they kind of mean by this. So you effectively have a body which is acting 100% efficiently, but only of an area of 0.9 square meters, for example. So moving on to the literature review of different diffusers' performances. So downforce is the force of lift acting downwards generating on the car. You know that. In motorsport cars, the generation of downforce is extreme as it enables the car to reach very high speeds while taking corners on a track. This forces the four wheels on the track onto the track asphalt, enhancing the grip, thus allowing the car to travel faster. Creating downforce usually costs drag, so in this case, induced drag, and we'll cover this in a second. So the amount of downforce needed depends on the track which is being driven on. Tracks with more corners will benefit from higher downforce to take these corners with a higher speed without slipping, while tracks with fewer corners and longer straights, downforce is needed but in a lower proportion. So let's talk about all these different factors here that they've covered. So first of all, they say creating downforce usually costs drag, in this case, induced drag. So why is that? First of all, you're manipulating the flow. And anytime you do that, there's going to be some sort of inefficiency, and that is crops up in drag. In this particular case, it's induced drag. And what is it? What is induced drag? So this is actually quite a tricky term to define in an aerodynamic sense in general, because each subfield in aerodynamics has like a kind of a little bit of a different idea of what they call induced drag. So to give an example, in aeronautical engineering, we always refer to induced drag as the velocity of the drag arising from circulation changes. So induced drag has a very specific equation, which is related to the gradient of the circulation. And in layman's terms, it means just how strong the wingtip vortices are. This is only ever produced when you have lift generation. That's why it's called induced. The lift is inducing this drag. Now, in vehicle aerodynamics, this becomes a little bit fuzzy. So in this particular case, it's a little bit easier to describe because we are creating downforce, which is a type of lift. There's a pressure difference, which is creating a force, and this is inducing drag as well. So anything that's coming from this object, because of it producing downforce, is technically induced drag as well. However, there are other parts on the car which produce vortices as well, but they're not technically induced drag. They are just vortex drag, and the reason why is because the strict sense of the word induced means that it comes from like lift or downforce production, whereas these vortices, which look like induced drag, are not actually coming from lift or downforce production. They're coming from just like flow being pulled and torn at the surface of objects, which create these vorticity and vortices. So you do see vortices on cars that look like induced drag, but not actually induced drag, and that's called vortex drag. Interestingly enough, when you are to measure induced drag in a wind tunnel or on CFD, you can use the exact same equations on both, but they're actually technically two different sources of drag. So that's what they mean by induced drag. So now they talk about the amount of downforce you need depending on the track. So if you have more corners, you want to have more downforce being produced by the car so you can go around the corners faster. Whereas if you go on a track with more straights and fewer corners, you don't want to have as much downforce. And the reason why is because downforce not only typically will come with the drag penalty, but also will come with a greater rolling resistance. So these two things will result in the car going slower on the straights. Whereas if you want to go around on the corners, then you want to have as much downforce as possible because the top speed of the vehicle is not nearly as important as the cornering speed. So those are the two variations in the vehicle setup. So now let's talk about the downforce generation mechanisms. So considering a symmetric armored body without a diffuser, so literally just a rectangular prism with the front rounded a little bit, located far from the ground in free air, no lift is generated on the body as there is no pressure difference from the upper and lower surfaces, as the air has the same velocity over both surfaces. So that's true. It's completely symmetrical, so there is no changes in pressure that the other side doesn't see as well. So it's completely equal. Now, obviously, with a bluff body, you will get vortex shedding. So the transient nature of the will mean that there is a periodic shedding and there will be a periodic lift, but over time, this will average out. When approaching the body, when approaching the body to the ground proximity, so when you put the body closer to the ground, air beneath the body suffers an increase in its acceleration due to ground constraints. In other words, as you get closer to the ground, you're shoving all this air underneath the armored body still, and because the cross-sectional area is becoming smaller, the air has to accelerate, and you get a pressure drop. This phenomenon is called ground interaction. So in figure 2, they have the variation of the lift coefficient with ride height with this armored body. And this is really cool. So I'll go through what they say first, and then I'll just talk about some little bits that um, need explaining. So closer to the ground, airflow acceleration beneath the body increases due to ground constraint, reducing the underbody static pressure further, thus generating greater downforce. Nevertheless, the increase in downforce with ride height decrease is limited due to fluid viscosity. These viscous effects are not dominant at larger ride heights, and for this reason, downforce is maximum at a certain low ride height. So what they're saying is viscosity is often a limiting factor in how quickly a fluid can move. And in this particular case, when you go down so far, viscosity then starts to interrupt the fluid's motion, and you can't really get it to move any quicker, and you don't get any greater drop in pressure, which means you don't get any greater change in lift or downforce production. That's why you get a sweet spot. If you go high, you don't really get that Venturi effect. If you go too low, then you get this viscosity interrupting this fluid. So there's a sweet spot. However, they say if lowered further, underbody flow resistance increases due to the viscous effects limiting maximum downforce. So in figure 2, the lift coefficient stops increasing when the ride height is close to 0. If lowered enough, flow viscous effects from the boundary layer on the lower surface become more significant, leading to a blocked area fraction of an internal flow. Viscous effects cause an increase in blockage area due to the increase of wall boundary layers and with velocity profiles occupying the largest fraction of the flow cross-section area. So what this means is when you get very close to the ground, you have obviously the boundary layer forming over the body because this is moving through the flow. And this means that so much of this cross-section area is actually taken up with this boundary layer, which is a slow-moving flow, so you can't really make it go any faster. And coming back to this figure 2, it's quite cool because they have the ride height plotted against the lift coefficient, and when you get closer to the ground, the lift coefficient increases dramatically. It's non-linear. It's I don't think it's quadratic, but it's definitely non-linear. But it gets to the point where you don't get any greater increase because of viscous effects. But by then, they're showing like lift coefficients or negative lift coefficients of like 2, which is quite cool. So moving on to figure 3, even though a body with a flat underbody can generate downforce in ground proximity, the presence of an underbody upsweep zone at the rear of the symmetrical body creates a cambered surface, resulting in a significant increase in downforce even for large ride heights. What does this mean? So if you have a symmetrical body, so the armored body without the rear diffuser, so just a rectangular prism, this is symmetrical. So when you get close to the ground, you have the Venturi effect effectively happening. But if you put a diffuser on there, now you effectively have a cambered surface when you think about it, because if you were to draw a line between, it's like halfway between the one surface and the other surface, so the top surface and the bottom surface, it'd be right in the middle of the body until you get to the diffuser, and then it'll start to jump up a little bit. So that's the camber line effectively. So that means that there is camber to this object. And if you have negative camber, it means you're going to get more downforce. So that's what they mean here. So in this figure, they have the armored body transposed onto the graph, and they go along the armored body's length, and they have the pressure coefficient plotted. They have a couple of points which are very important to note. As the air hits the front of the armored body, it obviously the pressure coefficient goes to 1 as there's a stagnation point there. But as you go underneath the body, the pressure coefficient drops to almost -2, and then it starts to increase a little bit, but it still stays negative, and this is due to ground interaction. Then once you get to the diffuser, it recovers, so you get the pressure coefficient going back to 0, so back to the free stream pressure coefficient effectively. So moving on to some cool results. I just paused the podcast there because I noticed that I didn't have any of the document highlighted that I wanted to. So let's continue. So we're going to go to the armored body and talk about the different flow regimes and their effects on the downforce being produced. So we have in figure 4 2 graphs. We have one which has they both have the same x-axis, so they show the ride height, so the distance to the ground. Then they have on one axis, on one graph, the y-axis is the lift coefficient or the downforce coefficient. The other graph is the drag coefficient. So from these graphs, they have 4 different conclusions. The first one is that the force enhancement area, so area A, which ranges from like being a ride height of one times the distance, like the diameter of the object, down to about 35% from the ground. So it's quite close. In this region, the lift coefficient dramatically increases. So there's obviously a major ground effect. So in this force enhancement region, as can be seen in figure 4, the first region, A, downforce increases with decreasing ride height. A symmetric pair of counter-rotating vortices with a high axial speed core and high levels of vorticity are present in the diffuser at the region. So let's look at figure 5, which has this. So they have the armored body, and as I mentioned, with the slant angle. So that when that slant occurs, you then start to get 2 vortices occurring, one on each side, and they're counter-rotating. And this is important for later. We'll see how this affects the downforce, but this is a major contributor here. Then in the next part of the process, so we have process like part A. In part B is where we lower the vehicle even more, and this is a plateau region. So the forces and the lift coefficient doesn't really increase very much in this area, and if the ride height is decreased, downforce stabilizes on the upper limit of the plot in a linear approximation. The diffuser flow remains symmetric. So the flow coming out of the diffuser is still symmetric, even though you have counter-rotating vortices, which in part would help that as well. However, the vortices increase significantly in size, and the vortex core has a low axial speed. In this region, ride height reaches a critical value. If we were to lower the vehicle even more, so we go to zone C, this is where force reduction actually occurs. So if you lower the height of the vehicle even more, we start to reduce the force here, the downforce. In this stage, the symmetric vortex flow within the diffuser breaks down, and the results in a separated asymmetric flow through the diffuser is shown in figure 6C. So let's move to this, where we have some oil flow vis. So this is where they painted the surface of the armored body, the underbody. And when we get into zone C, we get these 2 asymmetric vortices, and they're just like meandering around quite randomly almost, and to the point where they're actually inducing flow from one corner of the armored body instead of from the middle. So that would dramatically increase the drag and reduce the downforce produced. Finally, there is zone D. So loss of downforce even more. As the name states, if the ride height is decreased, reaching extremely small values, so near 0 millimeters, the generation of downforce is almost stopped. What happens is that the flow within the diffuser is totally blocked due to viscous effects for being so close to the ground proximity. So in other words, the boundary layer now that is forming on the armored body is really dominating this flow, as we covered a little bit earlier. So these are the 4 zones that the diffuser can operate in. Now moving on to the effects of the ride height a little bit more. They just have a few more sentences. So the ride height is defined as the distance from the flat underbody to the ground. As the diffuser ride height is gradually lowered, the flow behavior within the diffuser changes from attached to separated, and this influences the aerodynamic properties of the diffuser. Let's talk about the effects of the slant angle now. The slant angle, sorry. So the slant angle is this angle that I was talking about earlier, let's say 25 degrees, which is just the angle from the rest of the body to the diffuser section here. And in this paper, they're looking at 0 degrees, 10 degrees, and 25 degrees later on. We'll cover that probably in the next podcast because there's quite a lot more to go through still. So if the angle of the diffuser is close to 0, the boundary layer flow will not detach, so that's good. But the airspeed will not be reduced enough to make a laminar transition to the air at the end of the car when the 2 airstreams meet. So what does that mean? On the one hand, if you have too great a diffuser angle, as I mentioned, you will get flow separation. But if you have no diffuser angle, then when you have the flow from underneath the body reaching the free stream air, there's going to be a lot of turbulence because you effectively have a jet meeting the free stream. So when you have two streams of different velocities, you'll then get a shearing layer between the two. This is what they mean here, and this is results in a lot of like lost energy effectively. So if the diffuser has a very large angle, the boundary layer will detach and the airflow underneath the diffuser will become turbulent. So the angle of the diffuser is limited. When the angle is too small or too large, the diffuser will create more drag than necessary. So what about the effects of the vortices produced? This is a really interesting point here. They say the circular movement of fluid within the vortices contains a lot of energy. When these vortices appear, they roll up under the diffuser, taking high energy from the outside of the body and introducing it into the diffuser. However, they also take high energy from below the level of the body and mix it into the body of the airflow under the diffuser. This phenomenon enables the diffuser to function at high angles of attack without detaching or losing effectiveness. So what this means is it's very akin to vortex generators, where you are producing these vortices which take energy from elsewhere, pump it into the boundary layer, and allow the boundary layer to stay attached because the boundary layer is now moving faster, so it can overcome adverse pressure gradients, which would usually make it stall. Now, interestingly, the presence of a trailing counter-rotating vortex pair in the diffuser induces some level of upwash. Consequently, by Newton's third law of action-reaction, the downforce acting on the diffuser body is the result of the force reacting to the diffuser flow being redirected upwards by the trailing vortex pair. What does this mean? So what they're saying is you have this surface and you have this vortex next to it. You actually have two vortices, but let's just concentrate on one for now because it's the same thing for the other one. And what this vortex is doing is it's inducing flow around it to actually move up. So there's upwash underneath the diffuser. Then on the outside of the diffuser, there's obviously downwash because that's the other side of the vortex. But underneath the diffuser, this is very interesting because they say by Newton's third law, if there is upwash being created, there must be downwash somewhere. And because the diffuser is responsible for this vortex, there must be downwash around the diffuser somewhere, which means that there is sucking the diffuser down more. So this is actually an additional force that this vortex pair is creating through this upwash downwash mechanism. So that's really cool. In the force enhancement region, far from the ground, two vortices roll up, one on one side of the underbody and one on the other side of the underbody, as shown in figure 5. So we had that figure where you have the armored body, then on one corner you have a vortex, on the other corner of the diffuser you have another vortex of the opposite side. And I guess technically they should both be the same strength as well. So when both of these vortices originate on the corners of the diffuser inlet and expand as they move downstream on the diffuser ramp, moving inboard. So they start on these corners and they start to meander in towards the underbody of the diffuser and into the center part. Throughout this region, the flow is symmetrical and is attached on the diffuser ramp. And if the ride height is decreased, downforce increases. As the ride height is lowered, the main vortices move further to the interior of the diffuser and their size increases. A highly concentrated vortex core implies stable vortex flow. If ride height is further lowered, a separation bubble appears in the diffuser, which provokes a sudden increase of vortex size after separation, but also loses strength. Hence, downforce continues to increase. So let's look at this in the oil film flow viz. So we can see this on figure 6b, where we get these vortices kind of popping, and we get this separation bubble happening. Separation bubbles typically are low pressure as well. So this happens in the force plateau region B, which we've covered in figure 4, which, as we mentioned, when you have the object quite far away from the ground and you start to lower it, you do get an increase in downforce. Then when you go a little bit further, it starts to plateau and then it starts to drop off. So this is the plateau region. So this is where downforce decreases a little, but suddenly suffers an increase, reaching its peak at a critical value of a ride height. So there's a little bit of an increase and decrease. It wobbles around a bit, but it's mainly just a plateau. Below this ride height, the downforce starts to decrease. In this phase, flow is still symmetrical, but it is a bit disturbed, as shown in figure 6b with that oil film flow is the laminar separation bubble. So let's move on to what they're studying now, so their geometry. So in this paper, they're going to look at some CFD, and they have 3 different general types of armored bodies. Figure 7 shows the dimensions of the armored body with a 25-degree diffuser. So 3-dimensional CFD simulations are performed on an inverse armored body in order to observe the flow behavior under different diffuser configurations. This geometry is used as it is easier and faster to obtain reasonable results compared to a Formula One car geometry, in which the computational time and resources are considerably greater. The standardized model of the armored body is not used in this study, but the model is shown in Figure 7 with the corresponding dimensions in order to verify the results obtained. The first case study is an armored body without a diffuser, hence with a slant angle of 0 degrees. Then, this case will be compared with the configuration shown in Figure 8b, which incorporates a diffuser with a slant angle of 25 degrees in its bottom rear part with a diffuser length of 182 millimeters, so 35% of the total length of the body. The comparison between these two cases is interesting since it will be observed how the addition of a diffuser substantially improves the generation of downforce compared to the same body that did not incorporate one. The last geometry simulated is presented in Figure 8c. It consists of that same armored body with a 25-degree slant angle, but there are also 2 airfoils added at each side of the rear of the diffuser. The aim of the addition of these airfoils was to create a zone of low pressure at the back of the trailing edge of the body. So what they're saying is you have this armored body and we have the slant angle, the diffuser. And as we have the flow going underneath the armored body and then it goes to the diffuser, it starts to reduce in pressure. They want to reduce the pressure even further behind the armored body to kind of suck it through more, but also block it off from potentially other flow coming in. So they're using airfoils, which are aligned in a certain way to produce this suction zone effectively. So they have the cambered part, like the top surface, the suction surface, I should say, of the airfoils facing the body and the pressure surfaces facing away from the body. So that's how they're going to be approaching this. So that's the end of this podcast. I wanted to leave it here because we can pick it up later in the next podcast where we're going to look at the CFD setup and then the results. So it moves on quite nicely. So in this podcast, we've just covered the theory of diffusers and how they work, and how the ride height, vortex sizes, and slant angles affect the downforce produced, and also what they're going to be looking at for this study. So in the next podcast, which will come out in a few days, we're going to cover the results of this CFD simulation. So make sure to like, subscribe, and if you want to get better at CFD and or theory yourself, check out our courses in the link in the description. And if you want to get better experimental results, then check out the Atmosphere Hawk. It's an instrument that accurately measures the density of air in your experiments. And the reason why this is important is because the density of air changes by about 2 to 4% every day, throughout the day. And between days and weeks and months and seasons, it changes even more. So when you take your experimental results and you don't measure the density of air, you have that error in there, you don't even know it. So that's why most experimental results are trash. I said it. And then if you were to use those experimental results to validate CFD, you would have that error as well, because your CFD would have a different density to your experimental results. And in fact, let's say you took experimental results over the course of 3 days and you use all those results to hopefully accurately validate your CFD. Some stuff might line up, other stuff won't line up because the density is wrong. Because there'll be potentially some points in there where the CFD density coincides with the experimental density just by chance, but other parts won't. So some things may align, some things won't align, and you won't know why. So that Atmosphere Hawk gets rid of those errors for you, so you actually can remain sane and not go crazy trying to figure out why these things aren't lining up. So the link in the description is there for that, and it will save your sanity as well. So check that out. And I'll see you next podcast. Peace out, amigos.